Hi everyone, and welcome to lesson 2.1. Today we are going to shift our focus from arithmetic sequences to geometric sequences. Now, little reminder from your geometry days. We talked a lot in geometry about 30, 60, 90 triangles. So for instance, if let's say you had 18 as the length of your hypotenuse, you know you can divide that value by 2 to get the length of your short leg. And then whatever your short leg is, you can multiply it by the square root of 3 to get your value there as well. All right, what happens though if your value for this hypotenuse here, let's say this time it was the 9 square root 3, what would happen? Well, you still would divide it by 2 to get the value of your short leg. Okay, that still doesn't change. And you would still multiply it by the square root of 3 in order to get your longer leg, which in this case, square root of 3 times square root of 3 is just 3. And then we would make this 27 halves, right? So this is going back to some geometry knowledge. Now, why am I bringing this up here in pre-calc? Well, there's a pattern that they are deriving here on this lovely polar grid, which we'll talk much more about second semester polar grids. And we see this pattern starting here. And they are telling us that the length of our hypotenuse on this 30, 60, 90 right triangle for this first one is 8. And notice where this angle's at. This would be your 30-degree angle. This would be your 60-degree angle. So following that pattern we were talking about before, if we divide by 2 and multiply by the square root of 3, we would get our other two sides of our triangle. So decimal approximation of 8 is 8. And if we draw in now another triangle to start fitting our pattern, okay, this time we would draw this in. We're at 60 here. So again, we have another 30, 60, 90. Again, to get that side across from the 30, we'll divide our hypotenuse, which now is 4 square root 3, by 2, and then multiply by the square root of 3. So 2 times square root of 3 times square root of 3 is actually going to end up being 2 times 3, or 6. Okay, so again, our hypotenuse on this one ended up being 4 square root 3, which is approximately 6.93. Then this became 6. And then if we do it one more time, just to show the pattern again, continuously going, we again have a hypotenuse of 6 this time. Divide that by 2 to get our piece across from the 30. Multiply by the square root of 3 to get our piece across from the 60. So the next one is going to have a hypotenuse of 3 square root 3, which is approximately 5.2. Okay, so we see this pattern continuing on and on and on until we get to this point. And if you want to pause the video and copy the rest of this down, that's totally good. If not, we will continue on with this pattern. I will copy it onto the next slide for us to see. So why are we talking about this pattern? Okay, well, again, if we go to the next slide, our exact values from our chart here, starting with a sub 1, which is 8, go here. So we have that list going out. And if we start plotting the approximations of these, right, if we go down here, we have 8, 6.93, 6, 5.2. We start seeing these values 4.5 all the way down. And what we're going to notice is as we plot these, we have 3.9, 3.38, 2.92, 2.53. As we plot these, what we're noticing is that this is not a linear graph, right? There's that slight curve going down to these. So basically what we are able to see is that this is not linear. And more importantly, is this going to end up being arithmetic? No, okay, we are not. There's no consecutive decrease, right? We're not decreasing by a certain amount each time. We're not, decreasing. It's not linear. We don't have common difference. Any of that is happening on this one. Common difference. Okay, so what is happening here though? Okay, this is actually an example of what we would call a geometric sequence, right? And a geometric sequence is not when you are adding or subtracting, it's when you are multiplying or dividing by what we call this time a common ratio. Now, your common ratio is always actually going to be officially the multiplication aspect of this. To kind of offset the dividing, we are multiplying by a fractional value. Less than 1 kind of represents our division, okay? And similar to how our common difference was a sub 1 minus, or a sub 2 minus a sub 1, or a term minus its preceding term, that same idea is going to apply now for our common ratios, because we could take term 2 divided by term 1 to get our common ratio, or term 6 divided by term 5, or basically each time a term divided by its preceding term. Okay, so a little bit different than what our common difference was for our common ratio. So if we check out then, if we test this out for our previous examples, right? If we look back here, we said that a sub 2 was 4 square root 3, and then term 1 was 8. So if we test this out, we have 4 square root 3 divided by 8. This is going to reduce to be 1 over 2. 1 square root 3 over 2. And then if we test this out for another set, let's say we do term 3 divided by term 2. So we do 6 divided by 4 square root 3. Divide both terms by 2 again. Oops. I had these backwards. Sorry. 6 divided by 4 square root 3. We get 3 over 2 square root 3, which if we rationalize, multiply top and bottom by square root of 3, you get 3 square root 3 over 6, which again simplifies to be square root of 3 over 2. So we can check this out that we do in fact have a geometric sequence. Okay. Now, why are we doing all of this? Okay, well, we can also come up with an explicit formula for this as well. And we're going to look at a certain pattern here in order to do that. Okay, so what we're going to notice is if we take our first term, which was 8 from the original, and that common ratio, which we said was square root of 3 over 2, right? We just found that on that one. And we look at what each of these come out to be. So we had 4 square root 3, 6, 3 square root 3, etc. And we start putting this in terms of our first term and our common ratio. In order to get 8, we had to do the square root of 3 over 2 to the 0 power. This time, to get 4 square root 3, we'd have to take 8 times square root of 3 over 2 to the first power, or 8 square root of 3 over 2 to the second, 8 square root of 3 over 2 to the third. So each time we are taking our first term, our common ratio, and notice it's not the n power, it's always 1 less than our n power. So whatever n is, but minus 1. Okay, this is going to be our rule for the explicit formula for our geometric. Okay, so how can we actually use this lovely rule, right? So if you see here, we have this rule now written down. I would highly recommend that. How do we use this rule? Well, what we can do is use this, for instance, with the example that we had to calculate our further rules. So for part C on page 22, if I want the 11th term, okay, I'm going to plug in my first term, which was 8 for this one, my common ratio, which again for this one is square root of 3 over 2, and I'm going to take this to the n minus 1 power. My n this time is 11 minus 1. And I'm going to, back in math print, take 8 times the square root of 3 over 2. Make sure you use parentheses here. to the 11 minus 1 power, or you could have just typed to the 10th, and we get about 1.89, or if we turn this into a fraction, 243 over 128. Right, which is kind of making sense with our pattern. If we go back to what I had filled in, you notice that kind of every other one ended up being that fractional value as well. So that answer definitely can make sense for the context of our situation. So again, big idea of today, finding your common ratio, as well as using that explicit formula to find the value of a sequence for a geometric. All right, we'll work much more with these in class. Thanks for watching.